traditional chemist, ma'am.
Okay, perfect. So I have one computational chemistry slide in the entire slide deck, and I'm sorry I have to force it on you, but it is important.
Okay, no problem.
Okay, so a little bit about Cresset as a company. We're coming up on our 15th anniversary, and we've been growing 20% year on year since 2009, and that's around the time that I joined, so I take all of the credit for that, of course. We've got about 24 people now, and about half of us have PhDs. And in fact, interestingly enough, the design of the interfaces and the workflows of our software are all guided by the hands of a trained medicinal chemist, of a PhD medicinal chemist. So the heavy-duty stuff that's happening underneath is done by computer programmers and computational chemists, but the actual interface and how you interact with the software is guided by medicinal chemistry. So we're headquartered in Cambridge, United Kingdom. I'm based in Western Canada. I've got a colleague based in Toronto, and we also have an office in Bangalore.
Okay.
Okay.
Yeah.
So the types of industries that we work with, everything from pharmaceutical, biotech, agrochem, flavors and fragrances, and fine chemicals, so things like paints and coatings. So with medicinal chemistry, let's focus in on these two.
Pharmaceutical.
Yeah. So before we really get into this, and this is a good point for me to mention that please don't worry about taking notes. I'm going to send you this presentation with the notes pages that'll have written down pretty much everything that I say with every slide. But a little bit of bookkeeping. We have a newsletter that goes out about once a month. We do 11 releases a year, and you can get to it from this link. It's through our website. And it's really useful. We really try to make it to be scientifically relevant and, put out some interesting things in terms of case studies and posters and presentations that we've done.
Okay.
Okay. So let's get into the science. And the core philosophy at Cresset is we want to be able to develop ways to discover or view compounds and data in a way that you get results that you might have otherwise missed. And we want to be able to do this with a really easy-to-use interface with minimal learning curves. I'm as guilty as everybody else. I always take all of these software trials, and the icon sits at my desk, and I never open it because I think to myself, oh my gosh, I have to learn how to use this. And that's something we want to avoid. And you'll see this when I walk through the software with you. We've got GUIs, so graphical user interfaces, command lines, NIME nodes, pipeline pilot components, pretty much any way you can imagine that the software can be deployed, it can be deployed. Okay, so here's the science. So we really want to step away from looking at molecules the way we write them down on a piece of paper and think about ligands and the way that the protein receptor sees or experiences them. The protein doesn't care if nitrogen's a little blue N or oxygen's a little red O. The protein sees something that's got a distribution of electrostatics over a particular shape or geometry. Now, if we look at the electrostatic potential energy surfaces that I've got rendered here in the center, if we wanted to use those in a way to compare molecules, computationally that would be very expensive. There's a lot of data points there. So what we do is we condense those fields, those field surfaces into what we call field points. And these field points are placed at areas of local field extrema, so areas on these potential energy surfaces where the field is at a maximum value. Blue corresponds to... Did you have a question? Okay. So blue corresponds...
means we are narrowing down the space.
Well, you know what? It's encapsulating where is the field the thickest, which would be where is the hot spot for an interaction with a protein. Where is the most likely place? So I kind of think of them as interaction hotspots.
Mm-hmm.
So we use convention that red is positive, blue is negative. If you want to swap this is really easy to swap. You can make the negatives red and the positives blue if you like. Yellow is a shape or a neutral descriptor, and orange is hydrophobic. And you can think about this three-dimensional arrangement of field points, and the three-dimensional arrangement of field points really depends on the conformation. Now, you can think about this as a very information-rich but very concise pharmacophore that doesn't have any user in three, the positive, the negative, and the shape these are calculated from the potential energy equations. The orange ones, the
Okay.
hydrophobics, they're placed according to a set of rules, so parameterized functions.
Okay.
Okay. So here is the one computational chemistry slide. Underpinning all of our software, we're a molecular mechanics approach, but underpinning all of our software, we have our own force field. And our force field is different than the traditional force fields in the sense that we take the electrons off the nucleus. So we essentially put p orbital electrons into the force field with their own optimizable parameters. And that allows us to have an exceptionally good understanding of electrostatics. When I first saw this,
Okay.
and my background is in quantum chemistry, it's in density functional theory, and I thought this was really cool, a really cool way of getting that molecular mechanics to approach results that you would expect from a high-level quantum experiment, but with the sheep and dirtiness, the really quick speed of a molecular mechanics optimization. Okay.
Yeah.
So what this lets us get is, for example, we get pi-pi stacking correct because this allows us to separate the pi and sigma charges. So if you were to draw a phenyl ring and then put electron donating groups on one side and electron withdrawing groups on the other side, you can kind of have a tug of war between with what's happening with the electron cloud. So you can see the electron cloud changing quite substantially with substituents. And I've got an example here that I can show you. So if we start with toluene and we look at the fields, what we see is exactly what we're taught, that there's a pi cloud of electrons above and below the face of the ring.
Yeah.
Going around the outside, there's that positivity. If we put fluorine, then the fluorines will kind of suck the electron density out of the pi system. And then as we go down to chlorine, bromine, we're getting that electron density sucked out. But if you look down here, there's a bit of a hole in the negative field, and this corresponding to the sigma hole, where the pi electrons are being sucked out of the ring, but the sigma electrons are being pushed back into the ring.
Okay. Okay.
So if we put a bromine here, you would see a little blob of positive here associated with that sigma hole. And those halogen interactions are becoming, they're becoming much more interesting to medicinal chemists. Okay, so the key story on this slide is that we have our own force field, and it gives us an exceptionally good understanding of electrostatics.
Right.
So coming back to those field points, how we use them is for comparing molecules and aligning molecules. So instead of, when we're comparing two molecules, we don't look at the chemical structure. The protein doesn't care if it's carbon, oxygen, nitrogen, fluorine, whatever. It needs to have the right electrostatics and the right shape. So we use our field points. And what we do is we build up these cliques of field points, and we attempt to use those to do our optimization of the overlay between the fields and the field points. Now when we score according to the fields, and I will send you a copy of this article as well. This is openly available through our website, but I'll send you the link to it. So in this case, we get a field score. So this is electrostatics only of 0.66. 1 would be a perfect alignment, 0 would be a completely imperfect alignment. But we also take shape into consideration. So we use a combination of shape and electrostatics to give us a combined score. Now by default we use 50%, we do 50% fields, 50% shape, but that's something that you can change, you can modify that. Now there's two ways of looking at the similarity and the overlay. If you're interested in doing things like virtual screening and scaffold hopping, you'll find that you really focus on the score. Yes. However, on the other side, where we're really thinking about medicinal chemistry, where we may want to develop a binding mode hypothesis or understand a structure-activity relationship or do some stages of iterative design, I think we're much more interested in looking at the pose on that side. So it's really a combination of the two to help us get to the three questions of medicinal chemistry. What do I make next? Why do I, and have I looked here before?
Yeah.
So this is a good example, and this is really what Cresset's about, is comparing molecules. We're not just comparing molecules on a piece of paper, we want to compare them in a way that's biologically relevant. So if we've got two structures, and these are both crystal structures, they're DPP-4 inhibitors, they're low nanomolar. The 2D similarity here is very low. This molecule is really long and floppy, and this one's really compact. If we look at these in the binding modes and we look at the field point patterns, we see that the electrostatics of the core is largely maintained. We've got negative, negative, positive, positive, negative, negative, positive, positive, and we've got some minor changes out on the other side.
Yeah.
Okay, and if we look at the shape is more or less maintained as well. So even though structurally these are very different, the protein experiences these exactly the same way. So we want to be able to convert and interconvert structures. But then we want to go a step further and circle a bit that we want to replace and have the software suggest modifications that can be made that not only work at the fragment level, but also maintain the whole molecule bioisostericity. And we want to be able to do this in both directions. So this is really bioisosterism in the true sense of bioisosterism. That electrostatics, hydrophobics, and shape line up, not necessarily the connectivity of atoms. And we do these with our 4 products. These 3 products are desktop tools. Blaze is our virtual screening application. It runs on a cluster. And it's all about doing this whole molecule comparison of millions of compounds. On the other side of the equation, where you circle a bit that you want to replace and have the software suggest modifications from fragment libraries that could work in terms of maintaining the whole molecule field point pattern, we do this with Spark. So Spark is our scaffold hopper or lead optimization tool. The 2 products in the middle, I always think of Forge and Torch as being brothers, with Torch being the little brother and Forge being the big brother. Everything that Torch can do, Forge can do. And both of these products can do both sides of the equation, but in a more limited fashion. So with Torch, you can do whole molecule comparisons up to about 500 molecules. With Forge, there's no upper bound on the number of comparisons you can do. You'll be limited by the onboard memory of your laptop. You can also do this design stuff where you get rid of a group and you put in a new group with Forge and Torch. But the difference between doing this in Forge and Torch versus Spark is that Spark has databases of fragments. With Forge and Torch, this is where your ability as a medicinal chemist comes in. Did you have a question?
Nothing. Continue, sir.
Okay. So Torch is really all about doing iterative design. Now, what Forge brings to the table over and above Torch is the ability to build a pharmacophore hypothesis. So if you have a project where you don't have a protein ligand crystal structure, but you have some active ligands, we can take those, populate the conformations, and try to find a consensus alignment or a set of consensus alignments that you can go through and decide which one is feasible to take forward for a reference in another study. Forge also brings the ability to do 3-dimensional QSAR, both qualitative and quantitative. So we have a COMPA-like approach. I think our approach is a little smarter than COMPA, but we also have tools for doing 3-dimensional QSAR in a more qualitative way. So being able to summarize activity cliffs and really get a feel for, based on the structures that I have in my collection, what does an average active molecule look like in terms of the electrostatic shape and hydrophobicity? Where are my activity cliffs? What parts of the molecule, if I make something more negative, where am I going to get my boosts of activity?
Okay.
So is there anything specific, or should I just go through a medicinal chemistry workflow?
Yeah, please, you continue with your medicinal chemistry workflow.
Okay, perfect. So I'm going to hop out of the presentation, and again, I'll send this to you, and I don't know if you can see the little tiny type here. Every one of these slides almost every one of these slides have some notes associated with it. So when I send you the PDF of this, I will include these notes.
Dr. Mahesh.
Yeah, please.
Dr. Mahesh.
Yeah.
Sir, if you have any specific query, if you have any specific query related to your current research activity, it will be very easy for Dr. Ray to proceed.
Yeah.
So, do you have any query?
I'll ask.
Please.
No. Let me understand first your software.
Okay, sir. Please continue.
Okay. Yeah. I'll ask questions later.
Okay. So, what the example that I'm going to show, this is the training that we provided to a number of our corporate customers that have rolled out our tools to medicinal chemists. And what we really want to capture is the medicinal chemistry work. So the first thing I'm going to do is I'm going to launch Forge. And it'll just take a second here. And one of the things that you'll notice with our software is that there's a wizard. And the wizard guides you through the basic experiment. So initially when I started using the software, I used the wizard. Now that I'm using the software every day for the last 6 years, I use the wizard sometimes, but most of the time I work outside of the wizard. So the wizard's not mandatory, but it is a great way to become familiar with the software. So it asks us, it asks what we want to do. So I mean, we can view molecules in 3D. We can align molecules, which is what we're going to do. We can use activity miner. We can build activity models. We can fit molecules to an existing activity model that you may have made, or we can create a pharmacophore with field templater. Let's start with aligning molecules. So everything that you do with the software is going to start with an alignment of some kind. So it asks me to bring in a reference molecule. And there's two types of molecules in the Cresset environment. There's reference molecules and then there's idea molecules. The reference molecule is a ligand in a bioactive conformation. And that can come from a protein ligand crystal structure, a pharmacophore hypothesis, or even just bring in a molecule and minimize it and do some hand rotations. I never underestimate the ability of a chemist to hand design a potential bioactive mode that's there. You know, a lot of the times they're really, really good. So I'm going to bring in, I go to my folder here. It's on my desktop. This one. I'm going to bring an OIT bioactive. So these are cyclin. This is the ligand from the 1-OIT PDB structure. Okay. I'll bring it in, and I'll click next. It's asking me now to load the molecules to align, so I can copy and paste these from any of the drawing packages, or I can grab I've got an SD file here. I'll bring those in. Okay. It asks if I want to bring in the protein. I'm not going to bother bringing in the protein. I'm just going to click finish. Okay. Right. So we're going to do a basic alignment example here. Hello, are you still there? Hello, have I lost you?
Hello, Dr. Mahesh.
Hello.
Dr. Mahesh? Hello? I should call him on his mobile. Let me see what happened.
Okay, yeah, it sounds like his mobile might have dropped off.
Yeah, let me see. Any problem, sir? Okay, no problem. Okay, we will wait. We will. Okay, fine. Okay.
Hello.
Doctor, actually, the net is disconnected. He is connecting again. Yeah, he's back. He's back. Hello, sir. Hello, sir.
Hello.
Yeah, please continue.
Yeah. Sorry, ma'am. There was some interruption.
That's okay.
Yeah.
Okay. So what I'm doing now, I've got my 10 molecules from my SD file, and you'll notice that they're absolutely dead flat. And I've got my reference structure. So this is my ligand for my crystal structure. And the steps to doing the alignment are we do a conformation hunt and then we do the alignment. Now I'm going to do a quick conformation hunt here in the interest of time. Never ever use quick. I usually use very accurate and slow because I don't want to miss any conformations. If I show the option, you have complete control over how you do your conformation hunt as well as how you do the alignment. So here, if I wanted to dial up the shape similarity, then I could set this to 1. Okay. Now, I
Okay.
told you before that we don't look at chemical structure. Well, it turns out
Hmm.
if you have a series that has a common scaffold, then there's a lot of
Hmm.
value in having the maximum common substructure overlaid. But for this example, I'm
Okay.
going to do the alignment without any bias from the structure.
Right.
So this will just take a moment. So while this is going, I'm not connected to my VPN. I don't need the extra notes from the office to do this experiment. So a couple of
Okay.
things before we get into the results. You'll notice that there's some
Hmm.
color coding in the table. And the color coding
Yeah.
corresponds to specific ranges. So if this number is within a predefined range, so in this case activity, if it's within a good range, it's green. If it's outside of the range, it's red. If it's kind of on the border, then we color it yellow. And similarly, these are all
Oh.
controlled through our preferences and under the radial plot. So all of this
Okay.
information is there, and how they're weighted
Okay.
in terms of getting a multi-parameter optimization score.
Okay.
We have this radial plot, and this will come in when you start thinking about doing design and scaffold hopping and core optimization experiments, is that it's a way to plot multiple numerical parameters on the same plot so that when you're scrolling through results, you can quickly visualize the properties. So the way I have
Yeah.
mine
Yeah.
configured is that the smaller the area that's encased in green, the more drug-like or
Hmm.
more preferable my properties are. So for
Okay.
example, if I look at this one, everything looks really
Hmm.
good, but the similarity
Yeah.
is a little bit lower than I would like it to be.
Correct.
So if it's unfavorable, we plot it at the edge. If it's 100% favorable, we plot it at the center. And
Hmm.
you'll notice in the table here that this column sim is starting to fill up with numbers between 0 and 1. So these are my alignment scores.
Oh.
Okay?
Hmm.
So I'm going to stop this because I think the one that I'm interested in is done. Yes, it is. Good.
Yeah.
Cancel.
Yeah.
Okay. So if I overlay these now, I got a few that are
Hmm.
good. But what I can
Yeah.
start
Yeah.
doing, even at a glance, I can start getting a feel for what's driving the structure-activity relationship. I'm seeing that
Okay.
there's
Okay.
a bunch of positives here. If I turn the structures off,
Hmm.
whoops, let's turn the reference off as well. I can see that the
Right.
field points are
Correct.
starting to cluster together, so I can start to get a feel for what features could be driving activity.
Correct.
Now, the one I want to look at is this one. So if we look
Hmm.
at this one piezo ligand, it's got an alignment score of 0.584. And that's really low.
Hmm.
For molecules that are similarly sized about this size, I would look for 0.7 or higher. But in this case,
Hmm.
0.584, if we look at the alignment, we're only aligning with half of the reference. So there's
Correct.
all of these good potential interaction sites over here. So it's time to do some
Hmm.
medicinal chemistry. So here's where we really start thinking about doing medchem design. So let's do that.
Okay.
I'm going to right click and I'll edit a copy. Now, before I make any
Okay.
changes, the score is reported down in the lower left-hand corner, so 0.584. So,
Correct.
oops, I don't want to do that. Control Z. Let's turn my reference on. Now, I'm not a medicinal chemist. The
Yeah.
compounds in the fragments I design are absolutely brilliant in terms of getting the electrostatics correct, but I can't find anybody who wants to go into a lab and make them. So I'm going to cheat. I'm going to put a sulfonamide group on this amine here. I'm going to do exactly the same thing that's in the reference. So let's
Right.
start with putting a phenyl ring. And I'm going to rotate some
Okay.
bonds a little bit and try to get this, whoops, I
Hmm.
don't want to do that, Control Z. I'll try to get this lined up a little bit better. Whoops, come on, here we
Right.
go. I'll do a
Yeah.
quick
Yeah.
minimization and I'll optimize the alignment. So my score was
Oh.
initially 0.584. And by
Hmm.
making that little change, adding that phenyl group, I've increased my alignment score to 0.637. So this tells me I'm
Yeah.
on the right track.
Yeah.
Okay,
Right.
now
Right.
let's let's do something stupid here. Let's put a boron
Hmm.
and some stuff over here. So this is going to be a stupid example.
Okay. Okay.
Minimize and optimize the alignment. My score has gone
Hmm.
down from where we were.
Yeah.
So this is
Yeah.
where
Yeah. Yeah.
you can play with your hypothesis and the molecules that you scribble down on a napkin or on your fume hood cover. and get that little bit of feedback on whether or not your designs are going in the right direction.
Right.
And if I add this sulfonamide, I get this score up to about 0.85. If I'm happy with what I've done, I click OK, and then that shows up.
Yeah.
And usually I would
understood
move
this
these
concept.
around.
Yeah.
I would move this around to, I'd put it in a different place when I design, because I don't have activity data. So I would put this in its own section. If I want to get somebody to go to the lab and make this and do an activity measurement, then I can add that activity measurement in once it arrives. So this one might be 8.0, for example. So what you'll find when you start thinking about doing three-dimensional QSAR is that there's a lot of, I call it feeding the machine. So you take the data that you have, the SAR data, so the activity data that you have, you think about the structure-activity relationship, you do a new series of designs, you go to the lab, somebody makes them, somebody tests them, you bring that information back in, and you see if it fits in with the model. So with every QSAR model, there's going to be hypotheses that you're going to test, and hopefully you can really validate your model that way. And then as you get more active compounds, you feed that back in, and then the model becomes more and more refined.
Yeah.
Okay, so this was a basic alignment example, and I like to show this because this is the starting point. The next example I'm going to show you is a little bit different. And I'm going to leave the scaffold hopping for the very end. And I need to go to, is it in this one? This one. So I just opened another instance of Forge, and this is a gain cyclin-dependent kinase. And in this case, I've put an awful lot. I got 38 molecules, so it's not a huge data set. But in this case, I've aligned it to 2 references. So the 2 references, the reason I added the second one in is because I wanted to see if I could use this chain up here, this floppy chain up here. But these are fairly well aligned. So I've got all of my molecules aligned. What I want to do is start thinking about this in terms of mining out what the structure-activity relationship is. Now, I could approach this by doing a three-dimensional QSAR. So either doing the traditional COMFA-like experiment where I'm trying to get a predictive model. Well, it turns out that getting a mathematically predictive model can be very difficult. And it really comes down to, sometimes the data set's just too noisy, there's just not enough signal, you don't have a big enough activity spread. There's all sorts of reasons for it. So what I'm going to do for a model is I'm going to do this activity atlas model. What the activity atlas does is it goes through the Bayesian samples. So basically what we want to do is we want to look through what we know, so what molecules we have in the alignment, as well as their activities, as well as their pairwise comparisons, and see if we can devise a map of what average active molecules look like. And I don't know if I have this run or not, but we'll see. Yes, I do. Beautiful. So what comes out of this? And I like to look at my my most active molecules off.
Okay.
Okay, so this one on the left is my most active molecule. The one on the right is my least active molecule. So let me switch this over so I've got a little bit more real estate to work in. Now, the maps that come out of Activity Atlas look like this. Okay, so what this is according to these 38 molecules that I brought in and aligned, an active molecule looks like this. It's got this kind of U-shaped core of hydrophobics. It's got a blob of positive out here, a blob of negative here, some positive out here, negative, positive, negative. If I turn, and that's exactly the kinase motif, that negative, positive, negative. If I turn on my fields, I can look at my field points in the context of those maps. Now, it's quite possible that this positive field point here is somehow clashing with what we expect here. So that we can kind of start rationalizing out, even thinking about, okay, I've got this blob of positive here. an artifact because I've only got a small data set, or should I test this? Should I put something negative on this ring system and see if this is real? Because if I put something negative here, or if I put something positive here, if it's positive, then I should boost my activity. If it's negative, then I should kill my activity. So that's kind of the first map that comes out. The next map, and I like the next map a lot. These are our activity cliff analysis.
Okay.
So with the activity cliff analysis, the way these are read is that if the area is blue, then what it says is that if I put something negative here, then I'm going to get a boost in activity. Now, more negative can also mean less positive. So if we look at, for example, and in fact I'm writing a case study about this now. If we look at this, what is it, a pyridine ring?
Yeah.
So if we look at this, it looks like positive, then I should get a boost in activity. So that's my hypothesis. Well, I don't know what's been done in this data set. Now, if I wanted to test that hypothesis, what do? I put a whole bunch of electron donating groups here. So if I donate back into the pi cloud, then I should kill my activity. That's my hypothesis. I go into the lab. I mean, there's always you want to design better active compounds, but you also want to make sure you're testing your hypothesis at the same time. Similarly, the areas that are shown in green are favorable for steric bulk. The areas shown in pink are sterically hindered in some fashion. So it turns out that if we put a bigger group here, then we get a loss in activity. This is according to the 38 molecules that I put in. The final map.
This is almost similar, no?
You know what? It's similar in spirit to Compa. So the activity atlas model doesn't give you a number, a prediction of activity.
Yeah.
What it does is it gives you, it's you know what? It's a picture's worth 1,000 numbers. We do have an approach that's similar to Compa, where I could partition this data set into training and test set. And if I run that, I don't know what the results look like, but I can run it and show it to you. So in this case, I'm doing a field-based QSAR. So a field QSAR, it's got all the same, all the same stats as a partial least squares approach. If I run this, and I don't have a training or test set, so I'm just gonna have to look at the cross-validation. Now, our approach is a little different from Compa. So with Compa, if you look at the molecules in the alignment, what they do is they basically wrap it in mesh, and they'll sample at all the intersections of the mesh. We use our field point. So we use the positive and negative field points to sample for electrostatics, and then we use the atom positions to sample for volume. And the benefit of that is that there are way fewer points to sample. And if you look at this, I've already my model's finished. So it's lightning fast compared to Compa. When we validated this, we got as good as or better than Compa on all of the published Compa data sets. So in this case, I've got a 2-component model. I can look at the activity plot. This is not a realistic model. The data set's just not conclusive. It doesn't. It's not terrible, but I wouldn't be excited about publishing it.
Okay.
So, but we really want to focus in on the. Let me get rid of that. We'll go back to our activity atlas, the 3D view. The last thing that comes out is the regions explored. And the thing I like about the regions explored is that if I look at so this is the shape that's been explored. So if I look at my molecules, basically if I've got 10 molecules that have a contribution, either whether it's shape, fields, or electrostatics, or hydrophobics, in a particular region, we call it fully explored. So this gives us a feel for what chemical space we haven't looked at. So if I look at this in terms of the regions explored in negative electrostatics, so if I look at this, and then I look at let's go back to the average electrostatics of actives, I see that my regions explored line up really well with what my average actives are. Now, what this is telling is that these places where there's positive field points that are necessary for electrostatics, that I haven't really
Mhm.
looked at I haven't looked at putting something negative there. So it's showing me a limitation of my data set.
Yeah.
And it's basically telling me somebody has to go in the lab and make something.
Yeah. Yeah. Yeah.
Okay, so what I like to use these for is to do a spark experiment. So I want to be able to do a scaffold hopping experiment and look at my
Okay.
my new ideas that come through based on
Mhm.
what I told the software to do. So I'm going to do a
Yeah.
very simple scaffold hopping example.
No.
So
Please.
if I go to Spark, and what I'm going to do is I'm going to go back up to this one OIT reference ligand. I'll turn off the models
Okay.
because I don't want to copy it.
Okay.
I want this, and I'm going to copy it to my clipboard in 3D,
Okay.
and I'll go back to Spark. So Spark asks me, what do I want to do? I want to search for bioisosteric replacements. I'm going to bring in the
Okay.
molecule. I'll paste it.
Mhm.
Click next.
Mhm.
Now what I'm going to get rid of is this central bit here.
Right.
I do this different every single time that I do it. Now I can continue going through here and make some conditions on what types of atoms I'm willing to accept.
Okay.
I can add my protein. I can do field constraints. So I happen to know that this particular field point is absolutely critical for activity. I need this hydrogen bond donor, so I'm going to constrain this. So this has to show
Yes.
up in my answers, and I'll click
Yeah.
finish. So
Yes.
that's the basic setup. The next panel is
Mhm.
to figure out where do I want to search for fragments. So with Spark, we
Okay.
provide the Chembl fragment library that we've created, a set of fragment
Mhm.
libraries from zinc commercially available compounds. And we also have
Okay.
these e-molecules reagent databases. So these are reagents
Okay.
that have been from e-molecules that have been fragmented in a chemistry sensible kind of way. So if you wanted to
Okay.
exploit a particular reaction, you can use these
Mhm.
databases, and then as you're going through the results, you can get the ordering information for the reagent that you would need. I'm
Yeah.
going to look through the very common and the common. We'll give
Okay.
this. Actually, we'll just look through the very common. We'll do this quickly.
Okay.
So this will take about a minute or two.
Okay.
Okay, it's not connected to the Cresset engine broker, and that's okay. So similarly, the same type of layout in the interface, it'll have the same color coding, the same docs.
Mhm.
So for the things like the radial plot.
Mhm.
So once we get some results, we'll see this populate.
Okay.
Let me push this over. Results in tile mode. Okay, it's saying
And
3
one more
minutes.
the question I wanted to ask, ma'am. See, we draw the molecules, right? Hello.
You draw them? Yeah.
Ma'am, the molecules which are drawn should be in SDF format.
If you're working in ChemDraw or ChemSketch or IsisDraw, AccelerateDraw, you can copy and paste those directly, the 2D structures.
2D structures, it is compatible, right?
Yeah. So if you look on our website, in fact, I'll show you how to do this. So if we load up a browser here, Cresset-group, and under once this loads, under support, tips and tricks.
Okay.
So in this tips and tricks area of the website, there's all of these little short videos, and they're all about 2 minutes long. There's a video on a basic Spark experiment, how to transfer structures from chemical structure drawing packages into Torch. So in this case, I think I used Accelerus, ChemDraw, and ACD ChemSketch. And I just drew a bunch of structures, I circled them, copied and pasted.
Okay.
But there's all sorts of videos here, and I try to keep them at about 2 minutes long. If they're longer than 2 minutes, people don't watch them. But it's a great resource.
Yeah.
You'll recognize the voice of the person talking.
Yeah, I'll go through them.
Okay, so this Another
Yeah.
place to look for some really good tidbits is under science and case studies. The case studies in the poster. So any poster that we present at a conferences here, the case studies.
Mm-hmm.
I really like the case studies
Yeah.
because it's like reading a short journal article where it's like, here's the problem, this is how we solved it.
Okay.
And there's a whole bunch of them here.
Okay.
So using
Yeah.
activity atlas to figure out selectivity, for example. Three-dimensional QSARs, deciphering complex SAR. I think I wrote that one. Elucidating bioactive conformations. So there's a lot of information here.
Yeah.
And they're all very short. They're all 3 pages at the very most, including pictures. So for example, this fragment hopping with Blaze is, I think it's 2 pages long. 3 pages. No, 4 pages. So we keep them really short, really sweet. We try to make them as easy as possible to read through a lot of information quickly. So this is just finishing up the story.
And one more thing I wanted to ask.
Okay.
The software seems to be quite interesting. I'm very much interested.
Yeah.
And the thing is, ours is a self-financing institute.
So don't worry about the pricing and all those part.
And right now, I'm writing a proposal.
Okay.
Okay.
Yes, sir.
And I may get funding.
Okay.
Okay. So pricing and stuff, you need to talk to Yatizra. I don't even know what we charge for the software anywhere.
Dr. Mahesh.
But
Okay.
you can take if you take a software evaluation and you get some preliminary results that you can include in the proposal, we have no problem with you using those.
Okay.
Dr. Mahesh.
So since this is, I've already got some results from this experiment, and I'm running low on time because I do have to go to the airport to pick up my brother. So I brought some of these. Where did I put them? They're in here. Results from Spark. Oh, I'm in the wrong instance of Forge. I need to go to this one. So if I collapse these, I've got these results from Spark. So there's 4 results from Spark here, and I'll grid them so you can look at them. And these were ones that I thought were interesting, and it was a terminal replacement. So we replaced this bit.
Okay.
So we've got and there's a little bit of difference. There's no negative field here. Now, if I look at these in terms of the models, so if I look at the average electrostatics, what I'm seeing here with my Spark results that I chose, this one matches up quite well. This one matches up quite well. This one's missing that. So this might be a cause for concern. So it's missing the negative field point here. Now, if I turn my fields on, I see that that's the case, that there is really no negative contribution there. So what that's telling me is that this is a sample, this is an idea that's going to question whether or not my model is good or not.
Okay.
Okay, so it's going to test, is this blob of negative absolutely critical for activity? Let's go to the activity cliff summary. And it turns out that there's a little bit of a conflict here. So we've got more negative here and more positive here. What this is it's a limitation of the data set. So basically about 50% of the compounds have of the active compounds have a positive bit here. The other 50% have a negative bit here. And it comes down to the alignment. If you look at let me separate this. And I'll turn selected off. I don't need to look at the selected. I just want to look at the references. If I look at my references, what I see is that there's just a really slight shifting of this right here. And that slight shifting is kind of making our model a little bit wonky. So what that suggests to me is that I should probably go back and realign these to either one reference or the other and see if that sorts
Okay.
out that activity cliff issue. Because that seems, those two are really close. It's like, come on, model, what do you want? Do you want it positive or do you want it negative?
Okay.
Okay.
Hmm.
And there's
Yeah.
my Spark result that's finished. So usually what I would do is I would take my results from Spark, turn off
Hmm.
this back on, turn my references off.
Hmm.
I would look at my results from Spark and see how well they match up to what I'm trying to do. So
Okay.
it's another way of visualizing, okay, I've got these answers from Spark. So if I go back to the Spark
Hmm.
experiment, this is how we report our results. You can look at the raw results, the full table, clustered, the tile mode. I like the tile mode because I like looking at what fragments have I found. I've got my
Okay.
my radial plot again. My
Hmm.
references on. I like to separate them,
Hmm.
and I also like to look at the actual fields. So in this case, there is no difference. I found exactly what I came in with.
Yeah. Yeah.
Okay, this one is slightly different. So I'm missing a
Hmm.
nitrogen in that core ring.
Yes.
This one, I'm missing a nitrogen in the core ring, but in a different spot. In fact, I like this one better than I like this one.
Yeah. Yeah.
So I'd probably pick this one and call it a favorite so I can hang on to it. What's this one look like? This one, I'm
Oh.
interested in this one. And the
Yeah.
reason I'm interested in this one is because of this field point here. What this suggests to
Hmm.
me is that if I do a little bit more medicinal chemistry here, maybe I can force this to be a little bit positive here.
Okay. Okay. Hmm.
There we go. That's exactly what I wanted to do. I did a little bit of
Yeah.
medicinal chemistry. So changing that
Hmm. Hmm.
fluorine to a methyl group, it gives me something that's
Hmm.
more in keeping with what I know to be true.
Yeah.
And that's kind of how I visualize the results. I go through and I take a look and say,
Hmm.
well, that one's kind of interesting. A sulfazole,
Hmm.
interesting.
Yeah.
That one's kind of interesting too. A methoxylated core. I'm going to scroll down and see if I can find anything really exciting in here. It was only a single ring system, but there are some fused ring systems.
Yes. Yes. Yes.
Okay. So this is my bias. I love fused ring systems, and the reason I like them, in fact, I was talking to a guy earlier that the reason
Hmm.
we like fused rings is that we eliminate it. It takes a lot less time to do a confirmation hunt because it locks the confirmation.
Okay.
Okay. So this is something like this could challenge your
Hmm.
model to say, well, do I really have space to add more piece here?
Yes.
Can I push this to be a little bit positive down here? Can I see if there's any space I can get into? If I go back to that model again,
Hmm.
in that area that we explored, if I look at the activity cliffs in terms of space, it turns out that I
Hmm.
do have a little bit of room to explore in this direction. Not so much here,
Yeah.
but in this
Hmm.
direction. And
Yeah. Yeah.
if I were to bring this result over into Forge with Activity Atlas, then I could view this molecule in the context of the model.
Yes.
There's some good,
Yes.
there's some reasonably good
Yeah.
stuff in here.
Yeah.
Cyano groups are always interesting to me. That one's kind of cool.
Hmm.
So it's really all about finding, in terms of what we started with. If I go back to
Yeah.
my Windows docs, my starter. So this was a
Hmm.
nitrogen with a, a six aromatic ring with two
Yeah.
nitrogens.
Re-
This
Remembering.
group,
Hmm.
this group as a bioisosteer for this is not necessarily something that you
Okay.
would scribble down on a piece of paper. So usually the way I
Okay.
look through the results, if I don't see what I expect to see, so for example, if
No.
I'm doing a core replacement on something like a cyclic lactam, I want to see every one
Hmm.
of the 5-membered heterocycles. I want to see every member of the the 6-membered heterocycles. But where the things
Hmm.
that are interesting come in is when you get something that's a fused heterocycle and it's completely off the wall that nobody would ever scribble it down as a bioisosteer.
Okay.
That's where the value comes
Hmm.
in. So you really use this in kind of two stages of a project. At the beginning of a project, when you want to generate new ideas and get into new intellectual property space, and then at the end of the project, when you're writing up a patent and you want to make sure that you don't miss anything.
Yeah.
So I often call
this is very useful, this Spark.
Spark is really cool, and I think using Spark and Forge in tandem, and in fact I'll give you a sneak preview of what I'm working on for this month, is exactly what I've shown you here tonight.
Yeah.
The heart of medchem design, it's a relationship between Forge and Spark. And that's exactly what we're doing. So I'm writing this up now.
Okay.
So if you sign up for our newsletter, you'll get a copy of this automatically in August, the end of August.
Yeah.
So do you have any questions? Because I am running short on time.
Yeah, sure. I'll rush through my questions. One question I have clarified that whatever software we use for drawing, it is compatible. We can just bring in.
Yes, sir.
Copy and paste.
And ma'am, I wanted to know about the interpretation. See, this here, there is a pentagon.
There's a what, sorry?
Here in the results.
Okay.
What is that called as?
The radial plot.
Yeah. Radial plot.
So how to interpret that,
So
right?
in this case, I've got a 2D similarity, topological polar surface area, S log P, molar weight, and bioisosphere factor. So this bioisosphere factor is a rescaling of the score. So if it's 100%, it's really, really good. If it's 0, it's not really good. The way I'm configured is that the smaller the area in green, the more ideal my properties are. And you can change this using the properties. So this is completely customizable. You can add another spoke to the wheel if you want. So if we're interested in the number of atoms, we can add that as well. And as you're going through the results, so as I go through the results, I'm looking at the structure. So I'm looking at my fragment. I'm looking at my fields. But what I'm also looking at, so in this case, the 2D similarity is really, really high. Well, it's virtually the exact same group. So this may not be as interesting to me as I'd like, because I want my 2D similarity to be low, but I want my 3D similarity to be high. So some of these, the topological polar surface area is getting a little bit out of range here. It's not terrible. This one is terrible. So it's just a way to quickly visualize that properties all at the same time instead of struggling through a spreadsheet.
Okay. So these properties, is there any link with the Lipinski rule, whatever you have selected?
Yeah. So I can bring in, I've got a rule of 5 automatically calculated.
Okay.
So the rule of 5 for this particular one is really good. The rule of 5 for almost all of these is really good.
Okay.
When you start coming down to the bottom, you start getting into, well, the number of rotatable bonds is always going to be good in this molecule. It's not a terrible molecule. See if I can get any of those to be. Yeah, there we go. We got a big rule of 5 violation here. Let's take a look at what is it. Too many rotatable bonds.
Yeah.
Too floppy. So that's probably what our violation is. And that's the 499th down the list. So that's probably, I would probably not have gotten that far down the list. I probably would have did about 50. Just
okay.
Any other questions?
And one more thing, ma'am. You have shown all this thing results. Now, what basically I am lacking interpretation.
Okay.
How to interpret whatever result get.
Okay.
Kindly,
So usually the way the database, the file, the results are sorted, we sort them in terms of the score. So the tile is
Okay.
also reflected back in the table. So the score goes from the highest score
Okay.
to the lowest score. So this score is our alignment.
Okay.
So it's our field-based alignment. So
Okay.
if I overlay, and I do a lot of this. I'll turn this off for
Uh-huh.
now. So this alignment is really good. It's 0.996. Well, it should be. It's exactly the same,
Okay.
substituent.
Yeah.
This one is slightly different. Okay, so the field point here is missing. The score is a little bit lower. Not by very much, but it's a little bit lower. So what you really want to
Okay.
focus on when you're looking through the results, look for results that have a high score. Look for results
Okay.
that have good properties, and you can tell that from the radial plot. And the
Okay.
other thing that I look at in the results, I'll tend to, again, I'll put the fields on. So sometimes I'll pick a whole bunch. I'll look at the fields, grid them up and take a look at them. And a lot of the times I make them really small and I just kind of squint my eyes and try to find ones that look more or less the same. And then
Okay.
going a step further, I tend to look for ones even though they're not exactly what we want. So for example, this one going from that fluorine to the methyl group, this is one that I would
Correct.
look at because I can do something here. I can do some, well, I can't do it. I would have to rely on somebody else to do it. But something can
Yes.
be done here to modify this to try to make this more like this. So that's kind of the mental workflow that I go through when I'm picking out what ones I like.
Okay. Okay. Yeah. This
So
is all about for pharmacophore and QSTR. Everything is fantastic. What is there any? Docking suit.
yes. So this is recent. This is hot off the press. I'm going to go back and I'll show
Okay.
you where it is. And if you're interested in taking a trial, then we can arrange that with you. We've put a partnership in place with a company called Biomoltech, and they have a protein ligand docking software package called Lead Finder. And if you go to our website, there's some resources here. So they've done all of their validation, and they've published all of their stuff, their benchmarking. We've gone through and we've validated that their benchmarking is exactly what they say it is, and it turns out it is a really good docker. And Cresset is the sales agent for Lead Finder.
Okay. Okay. Okay.
It's a long and winding road. The guys that started this company are friends of mine, and they all have real jobs. But one of the things that because Schrodinger is so entrenched in the docking community, that in order to displace glide, you're going to have something that's absolutely amazing, and it's as good as, or and in some cases better than glide, but it's not light years beyond glide. So the pain to change just isn't there. But for a relationship with Cresset, where we don't have a docking engine, instead of us going back to the drawing board and making our own, having a partnership is a much smarter approach.
Okay. Okay. Okay.
So if you'd like to try this, we can set up a trial of this for you as well.
Please.
You got that, Yatindra?
Because
Yeah.
most of my work involves docking as well.
Okay.
My work, I'm using molecular docking as well in my work.
Okay.
So kindly send me the demo of that as well.
Okay. We can arrange that. So what I would do if you're using docking, so docking calculations generally take a lot of time. What I would do is I would encourage you to do the alignment experiment. So as you generate new ideas, align them to the reference, and if the alignment looks really good, if the score here looks really good, then cherry pick out the ones. I would cherry pick the ones that look really good in Forge, and then send those for docking. I wouldn't dock absolutely everything. I would use, because the Forge calculation is going to be quite a bit faster than doing a docking simulation, I would run
Yeah.
the forge, and then I would cherry pick out the ones that I think are good contenders, and then dock those.
Okay. Okay. Yeah. 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 You are right.
You can be a little more strategic about, okay, I'm going to try these ones, and if I get nothing from here, then I can go and I can test these ones.
Yeah. Mm. Yes,
So
ma'am.
I do have to go. If you have any
Yeah.
questions, please don't hesitate
Yeah.
to contact me. One of the things
Sure.
with our software, we want it to be easy to use. If you spend any more than 5 minutes trying to figure something out, then we failed in our design. So,
Oh, yeah.
okay?
Yeah.
So,
Yeah. Yeah.
and one of the things I didn't mention is that if you're not sure what anything does, I'll just open a random panel
Mm-hmm.
here. If you let your mouse hover,
Mm-hmm.
a little pop-up comes up that tells you what it does. So
Okay.
don't ever read the manual. The manual is available from the help menu, but I encourage you to never open it. I would sooner get an email
Mm-hmm.
or a phone call from you to ask a
Yep.
question, because then I
Yeah.
know that if it's confusing for you, then it's confusing for a lot of other people, and we need to fix that.
Yeah. 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 Yeah.
Okay? Excellent. So,
And one more request was there, ma'am.
okay,
You have provided me the demo, I mean, license for 1 month,
yep.
which is going to expire on 20th of this month.
Would you like an extension?
Yeah, please, please.
Okay. You'll have to ask Yatinder nicely, but I don't see any reason why we couldn't extend it.
Yeah, yeah, yeah. I'll ask Yatindra.
Okay.
I'll send a request mail to him.
Okay, and he will send that over to me, and we'll generate a key as soon as I wake up tomorrow morning.
No problem. No problem.
Okay, so I'm going to send you. So when when you're working through your trial, the files that I used today, if you would like these files to give them a try, I can send those to you as well.
Yeah, please, I think so.
Please, please, please.
Okay, perfect. You don't happen to have some graduate students that you can make do all the work?
Yeah, yeah. Right now I have 4 graduate students with me.
So better, sir, you should connect those students to us.
Excellent.
So I'll make them to work and learn.
Guy in India is extremely busy. So, and of course, if they have any questions,
Hello?
please let them contact me by email. I'm happy to help.
Yeah, yeah. Sure, sure, sure.
Excellent. So
Thank
with
you.
that, I'm gonna go. I gotta run to the airport, and then I'm coming home, and I'm going to sleep, and I will be awake in about 8 hours, and I'll send you the presentation as well as the files in the morning.
Okay.
Yes, ma'am. Thank you, ma'am. Thank you very much.
Thank you for your time. Have a good evening or a good afternoon, I
Yeah.
guess. Bye for now.
I think it's good afternoon. Yeah.
My time zone is
Have a nice
11 and a half hours, so.
Oh. Yeah, yeah.
Okay.
It's afternoon here, 11 o'clock.
It's 10, just about 20 after 11 p.m. So it's quite late.
Okay, okay.